Yesterday at the end, we were in a place where we were trying to examine, so you guys plotted your change in velocity here, and I was telling you about that this is going to be the average force times the time. That's the duration. That's how long the force lasts. And what we end up with is this linear relationship. And what this tells me is that if I do like y equals mx plus b, so the force times the time is equal to the slope, which we realized was the mass, and then your x is your change in velocity. So this is the average force. This is the duration. You guys know that word? That's how long the force lasts. The conclusion of your lab was the fact that the slope was the mass, and this is your change in velocity. So, over the past couple weeks, okay, we have been thank you. Over the past couple weeks, we have been working on this idea, this understanding that this mv thing was really important. And last week we called it the motion quantity. Okay? We call it the motion quantity. And this idea of a motion quantity, how much mass an object has and how fast it's moving, it turns out that that is actually a really important physics idea. And so we don't have to call it the motion quantity anymore. Now that we have a good sense of how it feels and what it looks like and what it means, this actual motion quantity is really the momentum of an object. Now, momentum is a physics term, okay? Momentum itself is a physics term. We use the letter P to represent momentum. And if you want to calculate it, you do the mass times the velocity. So an individual object that has mass and velocity will have momentum, okay? That's an important thing. And so this is how to calculate it mathematically. Conceptually, I think okay? So conceptually, as an idea, I think the momentum is a measurement of how difficult it is to bring an object to a stop. Does that make some sense to you? Like, think about a ball coming at you. Why would it be harder to bring to a stop? What would make it hard to bring to a stop? Yeah, if it's more massive, is it going to be harder to bring to a stop? Sure, think about someone rolling a basketball at you and then rolling a bowling ball at you. Which of those is harder to bring to a stop? The bowling ball. Why? It's so much more massive, right? It's so much more massive. All right? And what if you have two different bowling balls, or you have two bowling balls the same mass? What if one's moving faster? Harder or easier to bring to a stop? Much more difficult to bring to a stop. So this idea that the more momentum an object has, the more difficult it is to bring to a stop, that's our conceptual framework. Does that sound good? All right. Now, what are we working with over here, though? We're not working with just m times v. What are we working with? It's the m times the change in velocity. How do you change the velocity of an object? Well, what did we do in the lab? If you wanted to change the velocity of an object, you had to apply a force, and that force had to last for some period of time. So we have this as an idea, that if I want to change the momentum of an object, I need to apply a force, and that force needs to last for some time. Is that cool? And if you do that, basically what you get is you have the same object, so it has the same mass and the same change in velocity. So, if you want to change the velocity of an object, you have to apply a force, and it has to last some time. And if you want to measure the change in momentum, you need to know the mass and the change in velocity. And these two things, you could set them equal to each other like they are up here if you wanted, or you could just calculate it directly. Yes?
Can you explain the two equations in green again?
Sure. So, this is the momentum, right? So what does the little triangle mean? It's change. So if you want to change the momentum of an object, the object has a certain mass, and it's gonna, if it changes its velocity, you're going to get a change in momentum. But how do you make that happen? Well, you need to take a force, and that force needs to last for some long period of time. So to calculate it, you could take your force times the time, or you could take your mass times the change in velocity. Either way, you could solve for this. This has its own name, which I don't think helps, but it's on the sheet. This is called the impulse. So we use the word impulse interchangeably with change in momentum. Is that cool? Oh, that's so funny. Where should you be? We just sent you out? Like, get out!
We're doing
Bad kid alert. All right, you guys ready? So let's look at number 1. Okay, let's look at number 1. Number 1 says, hey, listen. You have two objects, A and B. They have identical velocities, but A has 3 times the mass of B. All right, so we want to know which one has, or compare the momentums of A and B. All right, check your neighbor real quick, see what your neighbor thinks. If you need to go, seriously, if you need to go chill out someplace, you can. Sorry. All right, what do you think? Noah, what do you think?
Object A is going to be harder to stop.
So just tell me which has more momentum.
Oh. Wouldn't it be A?
Why?
Because motion quality equals momentum. And doesn't that also have to factor with mass times change of velocity?
Well, it's just, if you just want to calculate it straight out, it's just mass times velocity, right? So which one has more mass?
Object A.
That's right. So if A has more mass, but they have the same velocity, which one's going to have more momentum?
A.
A is going to have momentum. How many more times? How much more? How many more times momentum?
3.
3 times. How do you know?
Because 3 times mass of object B.
That's all correct. So one of the things that Noah realized is if you look up at this equation, the exponent here is a 1 and the exponent here is a 1. Which means 2 times the mass is going to give you 2 times the momentum. That was excellent. All right, let's read B. 1B as in boy says, 2 other objects, C and D, have identical masses, but C has twice the velocity of D. Compare the momentum of C and D. Check your neighbor, meow. Yes, sir.
I don't want to see this backwards.
Yeah. Totally. Kennedy,
Hi.
how do the momentums of C and D compare?
Well, C's gonna have more momentum because it's twice in mass compared to D.
I think they have the same mass.
I mean, velocity.
So you say B or C is going to have more. Okay. How many times more? How do you know?
Because it's twice the intensity of D.
All right, she's money in the bank on this one. She said, look, she's like, they have the same mass, but C is moving twice as fast. Therefore, it's going to have twice as much momentum. Exactamundo. Right? Exactamundo. Good. All right, let's look at C. C says, two objects E and F where E has 4 times the mass and 1/4 the velocity. Compare the momentums of E and F. Check your neighbor, meow. Lila, what do you think?
I think E would have more momentum because it has 4 times the mass, even though like its velocity isn't like it's less, but it's massive.
So this is really interesting, right? So if we go to calculate this, let's look at E and let's look at F. So if I call F, the momentum is equal to mass times velocity, right? But what do we know about E? You said it's 4 times the mass, right? And what do we know about its velocity? So what happens if you multiply 4 times 1/4?
1.
So what do you think? So what's interesting about this is, if we think about it mathematically, they end up actually having the same momentum, even though E is 4 times more massive because it's 4 times slower, they can end up with the same momentum. So that's the thing I like the most about momentum, is that those are linear relationships. So if you're going 4 times as fast, you got 4 times momentum. How's that sound? Does that sound good? All right. So, if you want to find impulse, okay, if you want to find impulse, there's 2 ways to do it. You can multiply the force times the time, or you can apply the mass times the change in velocity. Both of those things will give you the impulse as an idea. Now, again, remember, we developed these relationships from that lab from yesterday, so they didn't just magically appear, right? We did a thing here. So, we're going to apply these to this next problem. Okay, we're going to apply these to this next problem. So it says, while being thrown, an average net force of 200 newtons acts on a baseball for a period of 0.7 seconds. Look at A. It says, what is the magnitude of the change in momentum? Scribble out the word magnitude. That's there to confuse you. They just want you to solve for the value of the change in momentum. Okay? So here's the deal. Anytime you're going to do a problem solving like this, really, we only have a couple different things we're looking for here, correct? I want to know, do they give us the force? Do they give us the time that the force is applied? Do they give us the mass? Do they give us the time? listen. You cannot distract. Listen, all you gotta say is okay. I wasn't asking for a dialogue. Just say, okay, no problem. All you gotta say. All right, so let's read the problem. It says, while being thrown, an average net force of 200 newtons acts on a baseball, mass 0.14 kilograms, for a total period of time of 0.07 seconds. Is that cool? All right, so tell me one thing. If I had to fill in one thing here, do you see one of these here, Natalie? Read the thing, do you see one of them? Okay, what's the mass?
0.14
Perfect. Lewis, give me another one. 2 what? Does it say 2,000 or 200? Okay, which one of those is this? It is the force, yeah. 100. 200 newtons. Fantastic. Jacqueline, I bet there's one more. Which one is that? Yes, look at you guys. Fantastic. All right, what's the first thing? Jacob, what's the first thing it asks for an A?
The momentum, the change in momentum of the ball.
All right, so Jacob, are we going to use, which one of these are we going to use to find the change in momentum? Or use FT or M delta V?
M delta V.
Well, let's check. Do I have M and delta V?
Actually, no. F delta T.
Exactly. So you notice that we have F and delta T already, so we can do that. All right, so let's do that. So the change in momentum, we can do F delta T. So 200 times 0.07, I bet that's 14. Now, the units are weird, okay? Because what am I multiplying together? I'm multiplying the force times the time, correct?
Mm-hmm.
What are the force units? Newtons. What are time units? So it's Newton seconds. It's a weird unit. Okay, it's a weird unit. So that was pretty easy, right?
Yeah.
Not too hard. All right, what does B ask?
Speed of the ball.
All right, so that should be okay. So when I have the other part here, right? So I have M delta V. So I know that the change in momentum is equal to the mass times the change in velocity. Now, we talked about this last week. What does the little triangle mean for us? What does the little triangle mean? It means change, and how do you calculate it? It's the other way around. So we're going to do final velocity minus the initial velocity. Now, if we think about the way the problem works, so here's our guy. He's going to throw his baseball. And he starts with it here. And he's going to throw it in an arc like this. And he's going to, oh. He's going to release it here, right? And so it wants to know how fast it's moving when it leaves his hand. So when you're throwing something, when you start back here, what's the initial velocity when you start here? 0, right? So do I know everything I can plug and chug in here? What's the change in momentum value? It's 14. What's the mass? Let's check over here. 0.140. The final velocity looks like that's what we're solving for, and the initial is 0. Put it in my calculator. So I solved for the final velocity, and that was 100 meters per second. So does that answer the question? What is the speed when it leaves his hand?
I'm kind of so how do you solve to get 100?
Oh, so I used my calculator. So I took 14 divided by 0.140.
Oh, okay.
Is that cool?
Yep.
Yeah. And so if I divide 14 by 0.140, it's 100. That may not be obvious, but that's what I did. So is this the speed it leaves his hand? And the answer is, yes it is. Yeah. Go real fast, please.